Hello, everybody. I wanted to go over our periodic table really quickly and just talk about how you understand or how you know what type of ion elements form. It's important to understand that pretty much looking at this darker line on your periodic table, and this is the same periodic table that I have shared in Google Classroom and in your portfolio. So pretty much from this point over, you deal with metals. Anything from this point to the left is considered a metal. And all metals form cations. These are your positively charged ions. Okay. Anything pretty much to the left is considered a nonmetal, which forms an anion, or a negatively charged ion, which makes ionic bonds the bond between a metal and a nonmetal. And as far as the periodic table goes, elements in the same group, same column, will form the same type of ion due to the number of electrons in its outermost shell. So all of these alkali metals here and hydrogen all form 1+ cations because they give away the only electron in its outermost region. Also, in the second column here, we have our 2+ ions because they have 2 electrons in their outermost region and therefore give 2 electrons away, becoming overall positive by 2. Now we skip through this whole middle section, which transitions us from the left to the right-hand side. And we can see that all elements in this column here will be a 3+ charge when in its ionic state. Now before we continue on, I wanted to go all the way over to the farthest right-hand column, and you'll notice that these do not have any sort of charge, and that is because they are noble gases, a cut above the rest, if you will. They are perfectly happy on their own and completely stable due to the fact that they have a complete full shell in their outermost region, so they don't need any other element to be happy, and they like to be by themselves, therefore do not form compounds typically. Okay, so these have no charge. You wouldn't find these in an ionic compound. Moving over just one column here, fluorine through astatine, you can see they have a -1 charge, and this is because they have 7 electrons in their outermost shell, which means they want to accept 1 more electron to be stabilizing that shell with 8 electrons in it, so they have a -1 charge because they take on 1 electron. And likewise, in this column here, we see that they form typically 2- ions, anions, negatively charged ions, because they have 6 electrons in their outermost shell, so by taking on 2 more negative charges, they become happy. And likewise here, we have a 3- for any of the elements in this group. And then these guys, because they have 4 electrons in their outermost region, they could give away 4 electrons and become positive by 4, or they could accept 4 more electrons and become negative by 4. And so you would know whether or not they were acting as a cation or anion by where they are in the chemical formula or in the compound name. The cations in a chemical formula and chemical formula and the actual name appear first, and then is followed by the anion, which is second. Okay. So what we're going to do is I am going to go through with you and tell you what the chemical formula should have been for each of the examples in our monatomics puzzle piece activity. Okay, again, it's very important to understand that cations, which are our positive ions, they lose electrons. They give away those negative charges to become overall positive. Whereas our negative ions are known as anions, and they gain electrons. They take on negative charges, so they are anions. Now, we had done this example together before you left our meeting, and just looked at the idea of calcium oxide, and looked at the ions that were formed in order to put calcium oxide together. So if you didn't know, you would use your periodic table, and so calcium is in the second column. Therefore, calcium produces a 2+ ion, so Ca2+. And oxygen, the oxide, is in the column way over here, which forms a 2- charge. So you have oxygen as a 2-. So now it's important for me to note that ionic compounds bond to make electrically neutral atoms. That means their charges have to cancel out. And because these two charges, a +2, cancels out with this charge here, a -2, they have 0 charge when they combine as is. Our compound formula would be written as CaO. So what I'm going to be writing on the side here is going to be a little bit different than what you're seeing here, because I won't write the number 1 in for a subscript. I only write them in if they're more than 1, which this activity did not have you do, and that's okay. So in this next one here, we're looking at sodium sulfide. I would look up what my sodium charge was. Sodium's in the first column, so it's got a +1. And sulfide refers to sulfur. If I look that up, I find that sulfur has a 2- charge. Okay? Which means because I need these to cancel out electrically, I need 2 of my sodiums to cancel out just a single sulfur. In this case, is another way to look at it. If you take the charge of 1 of the cation here, and you put it as the subscript for the anion, and you take the charge for your anion and put it as the subscript for your cation, you get effectively the same compound formula. It would tell me that I needed 2 sodiums for every 1 sulfur. Good. Now, I think it's important here when we're looking at the next couple of slides to understand where our Roman numerals are coming from. And that is because elements in the middle block of your periodic table, specifically known as the transition metals, these elements here do not get listed as a specific charge because they form more than one type of ion. They can be +2, +3, +4s, +thises, +that's, So you have to know which element you're talking about, or which ion of the element you're talking about, in order to effectively name it and to write its chemical formula. Okay? So if you are within the transition metals, you will have Roman numerals to represent the type of ion you are using in the formula, or in the name. Okay? So, in this first one, we see that we have iron 3 nitride. Now, you would need your ion chart in order to look up what iron 3 was for an ion. Now, your ion chart is in the Google Classroom at the very top, and so you would say iron 3, you would look it up, and it would be Fe 3 plus. Now, nitride is nitrogen. Nitrogen is in this group that forms a 3 minus. Oops, it's supposed to be an N. And 3 minus. And so these, as they exist here, are equal. Their charges would cancel. So I can write this as Fe(N). Nice and simple. For iron 2 nitride, however, iron 2, if you looked it up in your ion chart, you would see Fe2 plus. And again, nitride would be our nitrogen, which again is found in this column, so is a 3 minus. I can't just put these two together because they would be not neutral if we put them together. So we have to find a way to get these charges to equal each other. The easiest way I can show you to do this is to do our crossover method, where you would take the charge for ion and you would make it the subscript for nitrogen, so that would become N2, and you would take the charge for nitrogen and make it the subscript for iron, so Fe3. What this is effectively doing is saying I need 3 of these 2 plus charges to equal 2 of these 3 minus charges. In each case you'd have a plus 6 here and a minus 6 here. Now this compound is electrically neutral, as they all should be. Moving forward, sodium is Na, 1 plus. Chloride stands for chlorine, is a 1 minus. They cancel each other out, so it becomes NaCl. Lithium bromide. Lithium, first column, 1 plus. Bromine over here, 1 minus. So Li plus compared to Br minus becomes LiBr. Lithium bromide. Now, calcium bromide. Calcium is in our second column. Therefore, calcium holds a 2 plus, and bromine only holds a 1 minus. So again, these are not electrically neutral, which means I drop that 2 outside of bromine, and I drop that next to calcium, and I get CaBr2. Yes! Always interrupt. Looking at magnesium oxide, if I looked at magnesium, you would find that it is in this second group, which means magnesium is a 2 plus ion. Oxide stands for oxygen, which over here is a minus 2 anion. So you can see that these two cancel each other out just as is, so it's a 1-to-1 relationship for MgO. Okay, copper 3 nitride. You have to look up what copper 3 is on your ion chart, and I believe it is Cu3 plus. Nitride is an N3 minus. Because these are electrically neutral, it's again a 1-to-1 relationship. So Cu for copper and N for nitrogen. As we move further on, here we have copper 2 oxide. Copper 2 is a Cu2 plus, and oxide for oxygen is O2 minus. Again, they are electrically neutral and therefore become CuO. Now for the last 3, I cannot stress enough the importance of checking to see if your ions cancel each other out. If they do not, the crossover method is the best way to go. So this becomes Fe2O3. Sodium oxide, it's a 1-to-2 relationship, so we're going to see Na2O. And down here for magnesium phosphide, crossover method would be Mg3P2.